All right, when you're doing a titration, you want to reach the equivalence point. The equivalence point is when you have equal moles of acids and bases. If you are using an indicator, you want your endpoint, i.e. the color change, and your equivalence point to be the same. More reliable to plot it with a pH curve or a titration curve. So whenever you have a strong acid and a strong base, your equivalence point is going to happen at a pH of 7. So here's a graph here, and notice how we have a fairly flat region, and then we have a steep rise, and then if we keep going into the base range, we've got another fairly flat region. Okay? This steep rise can happen with the addition of 1 drop of base. Okay? And all strong acid, strong base are going to give you this same curve. Now, when you have a weak acid with a strong base, it's going to be different because it's a series of buffer problems. Your pH is going to be greater than 7 because that anion of a weak acid is a base, and then the weak acid completely reacts with the OH minus. So it is a buffer problem. But look at this, how you have more of a gradual rise, because this is your buffer region. Okay? And this not as steep as it was in the strong acid, strong base. Okay, so acid-base indicators. We write indicators generally as this because they're very, very complex. And there are lots of different ones. There's a chart in the book that shows the color changes over what pH ranges they change. So you want to pick one where the end point, i.e. the color change, is going to match your equivalence point. Okay, so you have pH equals pKa plus log of the indicator without the H over the indicator with the H to figure out what pH. We will have the indicator change color. You should notice that this is your Henderson-Hasselbalch equation. Okay? But in general, just find pKa of the indicator and you'll know plus or minus 1 is going to be where you have your color change.